Yeah. Okay, so today we're very happy to have Professor Charles Kane from the University of Pennsylvania, who will be telling us about the topology of the Fermi sea. Professor Kane, please.
Okay, well, thank you very much. It's always a pleasure to come to Chicago, so thank you very much for inviting me. So I want to tell you about the topology of the Fermi sea, and topology, this thing doesn't work. Does anybody know how to fix this? This has happened to me before. I did, but somebody else fixed it, so.
You might have to click on the screen. On the.
Yeah, there's some setting.
Maybe, does it work now?
Yeah, now it works.
Okay, great.
Okay, good. Thank you. Okay, so I want to tell you about the topology of the Fermi sea. Now, topology, as applied to electronic structure of materials, has a long story, which really started with the quantized Hall effect in a two-dimensional electron gas, where one can understand that a two-dimensional band structure, if you will, can be characterized by a topological invariant called the Chern number, and that shows up in a quantized in the quantized Hall conductivity. Okay, and so that discovery sort of initiated the study of topology in electronic systems, and there are more versions of this type of phenomenon. So for instance, in a three-dimensional topological insulator, there's also a topology of the band structure, which shows up in another kind of quantized response function. Now there are more caveats associated with this one. It's not quite as nice as the quantized Hall conductivity, but the point is that in systems with insulators, one could describe the topology of the sort of filled electronic states, the valence band, and that's a the sort of topology in Hilbert space, if you will, which describes the way the wave functions sort of twist as they go around the Brillouin zone. Now, the same kind of ideas can also be applied to metals. Okay, so for example, if you have a Weil semimetal, which is where you have the valence band and the conduction band touching each other at a point, then if you draw a surface around that Weil semimetal, it can have a non-zero Chern number, the same kind of Chern number that shows up in the quantized Hall effect. Okay, so there's a sort of topology associated with the twisting of the wave functions going around a Weil point, and that shows up in some kind of a term in the nonlinear optical conductivity of a Weil semimetal. Okay, and again, there are caveats as to when this type of thing applies, but this is another application of that topology. Another application is in a two-dimensional metal. The Berry phase that you pick up when you go around the two-dimensional Fermi sea also sort of shows up in the anomalous Hall conductivity. Okay, so this is not what I'm going to be talking about today. So what this is all about, this is about the topology that describes how the wave function in Hilbert space twists as you go around in momentum space. Okay, but metals also exhibit a simpler kind of topology, which is associated with the shape of the Fermi surface. Okay, and now I guess this is a little bit of a mixed audience. Some of you maybe grew up reading Ashcroft and Merman, and some of you probably didn't. But if you did read Ashcroft and Merman, you've seen this picture, which is the Fermi surface of copper. Okay, and so the Fermi surface of copper, it's a sphere, but it's a little bit too big for the Brillouin zone, so it has these little handles that go across, which makes the Fermi surface of copper have the topology of a genus 4 Riemann surface. Okay, and so the last 2 years ago, it was the pandemic, and I spent a lot of time sitting at home thinking. And
Reading Ashcroft and Mermin.
well, I've already read Ashcroft and Mermin, but I thought about this picture and I realized there's something topological here, and I asked myself the question, you know, what's the significance of this integer 4 for copper? Is there anything to that? Okay, and so what I want to tell you is the story of what I ended up coming up with about that question. Okay, and you know, we'll see where this leads. So the story I want to tell you. So the reason that I didn't give up immediately is when I realized that there's an example where I do know that the topology of the Fermi surface does have interesting consequences, and that's in one dimension. Okay, and so I want to go back and remember for you what how to think about one dimension, and this is going to be a discussion of the Landauer formula in one dimension, and then I want to describe to you my efforts at generalizing that to higher dimensions. Okay, and so this is going to lead into a discussion of the Euler characteristic of the Fermi sea, and then two applications of this. One is to a kind of nonlinear response in a two-dimensional system, which I'll describe to you, and a second is to come up with a universal characterization of the quantum entanglement in a Fermi gas or a Fermi liquid. Okay, and so the first story is in a paper I wrote last summer. The second story, we recently posted a long paper about the entanglement, and this is the work with my student, my PhD student, Pak-Man Tam, and also my colleague, Martin Klassen. Okay, so I want to start in one dimension. And so let me remind you how to think about one dimension. So if you have a one-dimensional wire, okay, then you can imagine passing an electric current through it and measuring the conductance. Okay, so this is what the Landauer formula is about. And you know, it's really quite simple. If you have just simple one-dimensional electrons with p squared over 2m dispersion, then the idea of Landauer is that the electrons are populated according to the lead that they came out of. Okay, and so if you apply a voltage here, then the electrons that are going to the right that came from this lead are going to be populated to an energy, increased by E times V, whereas the electrons coming from this lead are going to the left and they're populated here. And so that is just a simple matter to add up the current carried by each of the electrons. And so that's a simple integral of decay of the charge times the velocity. And the magic here is that the velocity is the group velocity, which is 1 over h bar times dE dk. And so what you can see is that the thing you're integrating is a total derivative. And so that just tells you that the current is E squared over h times the voltage. Okay, and so that's a quantized response in a one-dimensional system. Okay, now this quantization is actually, the argument that I'm giving here is almost the same as the argument that you would give to describe the quantization of the electrical current carried by the edges of a quantum Hall state. Okay, so it's the same argument. The only difference is that this is not quite as good because what it requires is the absence of scattering. Okay, so if an electron is going along to the right, it could bounce into impurity and bounce back to the left, and that would change this result. Whereas the beauty of the quantum Hall effect is that you spatially separate the left moving and the right moving electrons so that they can't backscatter. Okay, so this is it's sort of the same as the quantum Hall effect, but it's not as good. But the edge states in the quantum Hall effect, they are a topological property of the interior of the quantum Hall state. Okay, and you see here, I want to say that this is a topological property as well, but it's not a topological property of some two-dimensional insulating state. It's a topological property of the filled Fermi sea. Okay, and it is topological in the sense that, I can change the details of this dispersion. I can move it a little bit, and it's still gonna be the same. Okay, I can keep moving it until I cut the Fermi C into two pieces, and if I do that, then I'm going to get two of these, and so I'm going to get 2 times e squared over h. Okay, and so this Landauer conductance, this ballistic Landauer conductance, is probing a topological property, which is kind of a trivial topological property. It's just counting how many disconnected pieces does the Fermi C have. Okay, and so that's what that's the topology in one dimension. Okay, and so the question then is how does this generalize to higher dimensions? And so let me describe a generalization of that. So this counting the number of disconnected pieces, this is what the one-dimensional Euler characteristic is. And so let me tell you about the Euler characteristic. Oh, before I do that, let me just say, I told you this is not as good as the quantum Hall effect because it requires perfect ballistic transport, but that doesn't mean you can't see it. Okay, and in fact, there are famous experiments going back to the 1980s and 90s where precisely this quantized Landauer conductance was observed in quantum point contacts, sort of lithographic quantum wires, carbon nanotubes, semiconductor nanowires. So this, so it doesn't have to be that perfect in order to be able to see it. Okay, so it's not as good as the quantum Hall effect, but it's still good enough. So, okay, so let me tell you about the Euler characteristic. So, so this is a general thing that you learn about in math class. And one of the formulations of the Euler characteristic is in terms of the Betti numbers, which sort of count the number of cycles, closed cycles that you can have in the system. But let me just say, so if I apply it to Fermi surfaces in one dimension, what this Euler characteristic, it just counts the number of components of the Fermi surface, precisely the thing that the Landauer formula is counting. In 2 dimensions, if you have a 2-dimensional, Fermi C, then this Euler characteristic counts the difference between the number of electron-like Fermi surfaces, the ones that enclose electrons, and the number of hole-like Fermi surfaces, which enclose empty states. Okay, and so that's the 2-dimensional case. In the 3-dimensional case, the Euler characteristic of the Fermi C is related to the genus of the Fermi surface. Okay, distinguishing like the Fermi surface being a sphere or being a donut. Okay, and so there's a formula you could write like this. So actually, one thing I'll say is that the Euler characteristic, you can either talk about the Euler characteristic of the Fermi C, which is the set of occupied states, or you could talk about the Euler characteristic of the Fermi surface, which is the boundary of the Fermi C. Okay, and they're related to each other. In odd dimensions, the Euler characteristic of the Fermi surface is just twice the Euler characteristic of the Fermi C. And in one dimension, this is obvious because every Fermi C has 2 boundaries, right? And so so the number of disconnected components of the Fermi surface is going to be twice the number of disconnected components of the Fermi C. In 3 dimensions, you can, maybe the formula for the Euler characteristic of a surface in terms of the genus. There's a 2 here. Okay. In 2 dimensions or any even dimension, the Euler characteristic of the Fermi surface is equal to 0. So, for instance, in 2 dimensions, all the Fermi surfaces are just circles, and those are trivial. Okay. So somehow the Euler characteristic of the Fermi C has a little bit more information in it than the Euler characteristic of the Fermi surface, at least in 2 dimensions. Okay, so another way you can think about it, which is the way I like to think about this Euler characteristic, is you can think about it in terms of the critical points of the electronic energy dispersion. So this is the subject of Morse theory, and the energy, E is a function of K, is a Morse function. Okay, and you cut it with a Fermi surface, and you get you cut it at some energy, you get the Fermi surface, and so what Morse theory tells you is that the topology can be related to the critical points, and it's basically adding up the critical points with a plus or a minus sign depending on the signature of the critical point, which basically counts the number of downward directions. Okay, and so what this tells you is that maybe something that should be obvious, which is that this topological invariant can only change at a transition where one of these critical points passes through the Fermi surface. Okay, so this is called a Lifshitz transition. And so, for example, if you start off, if you have a energy that has a saddle point in it, then if your Fermi energy is below the saddle, then it's split into two pieces like this, okay? And if you raise the Fermi energy above the saddle, then those two pieces connect to each other, and that's a change in the topology of the Fermi sea, okay? And so Moore's theory tells us exactly that the Euler characteristic changes by 1 at that transition. Okay, so this is the topology of the Fermi sea. Now the thing that I want to show you is a kind of generalization of the Landauer formula from 1 dimension to 2 dimensions. Okay, and so again, let me recast the 1-dimensional Landauer formula. So it says that the conductance is this invariant times e squared over h times the voltage. The current is related to the voltage. I can also write that if I wanted to in terms of the charge. So the current is just the time derivative of the charge that is accumulated on the right. Okay. And so that says that I can write this charge response function as e squared over h times this Euler characteristic divided by the frequency. Okay, and so what I want to try to argue to you is that a generalization of that is so in 1 dimension, I divide my system into 2 regions and apply voltages across them. Now what I want to do is I want to divide my system into 3 regions, and I want to apply voltages to 2 of them and measure the current in a third. Okay, and so I can cast that as a charge response in the 3rd region in response to voltages on the first 2. And so what I want to argue to you is that this defines a response function which has a particular frequency dependence and picks out the Euler characteristic of the Fermi sea. Okay, and so I'm going to give you a couple of arguments for why this is the case. So in order to do that, let me sort of warm up by again giving you another explanation for this Landauer conductance. And so I want to introduce a thought experiment. And so what I want to do is I want to take my infinitely long 1-dimensional wire, and I divide it into 2 regions, and I want to apply a voltage pulse to one of the regions. Okay, and I'm going to apply a voltage pulse in such a way that the time integrated voltage is h over e. Okay, and so then I want to ask what happens. Okay, and so it's not too hard to think about what's going to happen. So this voltage pulse is going to give a little kick to the electrons. It's going to give an impulse to the electrons, where there's going to be a net change in the momentum, which is the integral of the force. Okay, and so it's not too hard to see that this impulse is going to be precisely equal to 2kF, where kF is the momentum spanning the Fermi surface. Okay, and so the effect of this impulse is to transfer one electron from one side of the Fermi surface to the other. Okay. Another way you can see this is that applying this voltage pulse. If I was to this voltage pulse is very similar to the argument that Laughlin introduced to explain the quantization of the quantized Hall effect. So there, what he imagined is threading a h over e flux through a hole, and if you imagine sort of putting this into a circle and thread an h over e flux, then this is precisely what you do. And so when you do that, what happens is that, if I put it in a circle, then the momentum is sort of discrete, and it moves every electron over by 1 space. Okay, and so at the end of the day, every electron is moved over by one space, then you have one extra electron here and one missing electron here. Okay, and you know, so when you say it like this, this is really reflecting an anomaly, which is the sort of lack of conservation of the charge of these right and left moving electrons. Okay, and so this this charge that changes in response to this voltage, this pulse, sort of reflects the chiral anomaly. Okay, and how does the chiral anomaly happen? How can it be that the charge of this left mover and the charge of the right mover are not conserved? The reason that happens is because the left and right movers are connected to each other precisely at the points where the velocity is equal to 0. Okay, and so another way we can think about this is that when we apply this voltage pulse so that every electron moves over by one space, then the only place where anything happens is where an electron changes its direction from going from right to the left. And so what you can see is that, so in the picture I drew, there's an electron that goes from being a left mover to a right mover, an electron that goes from being a right mover to a left mover, and so there's 2 minus 1 electrons change direction. And so at the end of the day, exactly 1 electron is going to the right, and so exactly 1 electron goes into this lead. Okay? And so I can think about that by counting the number of electrons that change directions. Okay, so this explains this Landauer conductance. And you can see that it's sort of related to the critical points, which is like what happened, it's like thinking about the Euler characteristic in terms of Morse theory. Okay, now, so what I want to do now is I want to sort of step this up to 2 dimensions. So I need to have 3 regions now, and I'm going to draw these in the simplest way that I can. I'm going to suppose, first of all, that one of these regions is sort of straight. Okay, and the other 2 are just the other 2 quadrants. Okay, and so I want to do this. So now what I want to do is I want to do a sequence of voltage pulses. So I'm going to apply an H over E pulse to this region, followed by a H over E pulse in this region. Okay, and so for the first pulse, so what happens after the first pulse? Well, so this is where it's nice that I made this a straight line because now this boundary has translation symmetry, and so I can think of every value of ky is going to be independent, and every value of ky is just like the one-dimensional problem that I told you before. So for every value of ky on the Fermi surface after the first pulse, there's going to be 1 extra electron moving to the right. And then there will be a hole moving to the left, but that's going off in the other direction, so we don't care about that. Okay? So after the first pulse, I have 1 extra electron in all the sort of blue shaded regions here. Okay, this is sort of a hypothetical Fermi surface that has a couple of holes in it. Okay, so then the question is what happens when I apply the second pulse? Okay, and so and what I want to ask is how much charge flows into this region, subtracting off the contributions from having the pulses act independently of each other. So what's going to happen is what I need to do is I need to take these electrons, these sort of extra electrons that are moving to the right, and I need to ask, in response to the second pulse, how many of them change directions? Okay, and those electrons are going to change directions if they're sort of on the side here, where the y component of the velocity is equal to 0. Okay, and so if you look at this picture, you can sort of see there are 1, 2 where it changes going up, and 1, 2, 3 where it changes going down. And so the net difference is going to be -1. And that is precisely the Euler characteristic of this Fermi sea. Okay, and with a little bit of effort, you can convince yourself that this works for any Fermi sea.
Is there a local version of this formula where instead of the total net charge, you're just considering the change in the charge density as a local quantity?
Not that I know of, no. There is something that will be sort of local that I will tell you about in a little bit, but it's not precisely this. So I'll try to point that out when I get to it. But as far as this response function is concerned, this is the only version of the response that I know. Okay, yeah, that's a good question. Okay, good. Any other questions? All right. Now, so this is a sort of a hand-waving argument, we can back that up with two different kinds of calculations. And so I don't want to go into the technical details of these calculations too much, but let me just tell you what they are. So one kind of calculation is based on a semi-classical transport theory, the Boltzmann equation. And the Boltzmann equation really is sort of the right theory to describe the collisionless transport in a Fermi gas. Okay, so we're assuming there are no there's no scattering. Okay, and so you can write down the Boltzmann equation, and it's not too hard to put the pulses in with an electric field, and then do a perturbative calculation. And that perturbative calculation, basically precisely reproduces this pulse argument that I just gave you. Okay, and it also allows us to generalize this calculation to describe, instead of having pulses, these h/e pulses, we can have the voltages in the frequency domain as a function of sort of oscillating voltages, and we can also relax this assumption I made about the angles, and so we can do it for arbitrary angles between these regions. Okay, and so one can show that that this result sort of remains the same in each of these cases. Okay, so that's one set of calculations.
Actually, have to be straight line.
Yes and no. If they're not straight. Now, if it goes out to infinity, then I think they sort of have to be straight. Okay, they have the limit. There has to be a well-defined limit, and then if they're not straight in between, then that will put a limit on the frequency regime where this is valid. So this will be valid at low enough frequency that you're sensitive. Or you could imagine if it's straight for small distances and then starts to curve, then there will be a different frequency regime where this will apply. But I think if you have a point here, there's always going to be some region near the point where it's straight. Okay, and so I'm banking on the idea that there is always a regime where this will be right. But it does, but this does describe the straight case. But there is always a straight limit. Yeah, that's also a good point. Okay. So so one other family of calculations one can do is to do the quantum theory of this, where we have a Hamiltonian, which is free fermions, and we can put on a perturbation and then do the generalization of linear response theory, sort of nonlinear response theory, just do perturbation theory. And so what that amounts to doing is to calculating these three-legged bubble diagrams for the fermions, okay? And there's a sort of standard technology for doing that. And what I will say is that in a slowly varying limit, this precisely reproduces the Boltzmann theory. Okay, and so it's nice to be able to do this, but we didn't really learn anything new that we didn't already know from the semi-classical theory for this. Okay. So so we have this calculation, and so it's a fair question to ask, is this something that's even in principle possible to measure? Okay, and so I think the honest answer to that is it's probably going to be hard. It might be possible, but there are issues. And so let me just tell you what a couple of those issues are. So one issue is, in order to do a measurement, you always have to do some measurement with electrical contacts. And that puts a bound on how low the frequency can be. Okay, so if you think in terms of this pulse argument that I gave you, if I apply a pulse and I have some system with leads, I apply the pulse and then I wait, get a cup of coffee and come back and apply the second pulse. The first pulse is just going to be completely gone by the time I apply the second pulse. Okay, so there'll be no correlation between them. So, and in the frequency domain, that puts a lower bound, the size of the system puts a lower bound on the frequency, okay? And of course, we don't want the frequencies to be, bigger than the Fermi energy. And so there's a delicate sweet spot of frequency that one has to be able to achieve, okay? And that's a technical challenge for any experimentalist. There's another issue, which is the role of electron-electron interactions. Yeah?
Why omega 2 has to be much larger than omega 1?
Good. So there's another issue which I didn't measure, which is that there's another term in the response, which is like 1 over omega squared, 1 over omega 1 squared. Okay. So and that term is also present. So what this term comes from is it comes from when the two pulses happen at exactly the same time. So in this pulse, when I do the real time pulses, the result that I gave you is right, but I make care to not have the pulses be exactly on top of each other. If the pulses are exactly on top of each other, then there's another term. And that shows up in the frequency in the frequency domain response as a 1 over omega squared. Okay, and so so this inequality is making it so that the intrinsic response dominates that extrinsic response. That's the answer. Okay, good. So then there's another issue, which is if you have interactions, and it's not too hard to see that this this response, which maybe is described by this three-legged bubble, is going to be modified by interactions, which can be corrected with these sort of RPA-like bubble diagrams. Okay, and these do give a correction to the result. Okay, so this quantized response is not going to be quantized anymore in the presence of Fermi liquid interactions. Okay, so in order, and this is actually something that we even already knew in one dimension. If you have a one-dimensional Luttinger liquid, if you calculate the frequency-dependent conductance at a frequency bigger than V over L, then it picks up the interactions through the Luttinger parameter K. Okay, and so this is something we already knew even in one dimension, that the one-dimensional Landauer conductance at finite frequency is modified by interactions. Okay, so if there's any hope of seeing this, we need to be in the right frequency regime, and we need to have a system that's weakly interacting. Okay, maybe there's some hope. So let me just give you my best guess here, which is to think about a plane of graphene, and you can imagine having your plane of graphene with three sort of metallic contacts sitting on top of it, And you know, if you're sufficiently close to the Dirac point in graphene, then the interactions will be weak because the density of states is small at the Dirac point. And if you tune between the you know, above the Dirac point and below the Dirac point, the Fermi surface goes from being electron-like to hole-like. So the Euler characteristic changes. And so if you can get into the appropriate frequency regime, then we predict that there should be this quantized jump in the nonlinear conductance. Okay, and so you know, I think this is a challenge. You know, there are many experimental challenges that would have to be overcome to be able to do this, but maybe there's some motivation to try. Okay. So so what I'd like to do in the remaining time is tell you about a second idea we had for where this topology of the Fermi surface might show up in some physical quantity, and that has to do with the structure of the quantum entanglement in a Fermi gas. And so our motivation for this is that you know, it's well known that you know, measures of the quantum entanglement can tell you deep things about the structure of quantum states. Okay, and so an example of that, you know, is Michael Levin and Wen and also Kitaev and Preskill introduced this concept of the topological entanglement entropy. And that shows that you know, there's a measure of the quantum entanglement, and so one version of that is this mutual information that characterizes three regions, and that's related to the total quantum dimension d, which is an integer that gives a topological characterization of some you know, two-dimensional gapped topological phase of matter. Okay, so that's an example of this. There's another example, you know, of course, this is in a gap system. In a gapless system, in a one-dimensional conformal field theory, then it's well known that there's a universal term in the bipartite entanglement of a one-dimensional conformal field theory, which has a logarithm, which diverges logarithmically in the system size and is proportional to the central charge C. And C is also a sort of a topological quantity that characterizes the low energy degrees of freedom, the low energy gapless degrees of freedom. Okay, and so now, you know, in a one-dimensional Fermi gas is sort of the simplest kind of one-dimensional CFT, which has, you know, C is just equal to the number of components of the Fermi surface. So C is precisely this Euler characteristic of the Fermi C. Okay, so so the question is, can we come up with some sort of a generalization of this? And so this is actually something where people have sought to generalize this Calabresi result to higher dimensions. And so one version of that, if you consider the bipartite entanglement of a, you know, d-dimensional Fermi gas, then what you get is you get an area law, basically. So it's an area law with a logarithmic divergence. And, you know, this is actually, it's fairly simple to understand this result because, you know, you can imagine that you have, let's imagine you have periodic boundary conditions in d-1 of the dimensions, and then there's one dimension where you do the entanglement cut. So then, since I have periodic boundary conditions in all of the perpendicular directions, I can think about each value of k independently, and each value of k is just going to be a one-dimensional system that has the Calabresi log, and so it's going to be this log times the number of one-dimensional modes in the Fermi surface, and that's just going to be kf times L to the d-1. Okay, it's just going to be the real space area times the projected area of the Fermi surface. Okay, and so so this is so this has been known for some time. Israel Klitsch introduced this. So there's a log divergent area law, but this isn't what I'm after. It's not topological in the sense that it depends on KF. Okay, so I can smoothly change my Fermi surface, and this thing changes continuously. And it also it doesn't distinguish sort of one-dimensional entanglement from d-dimensional entanglement. So you could imagine a system where you have just perfect one-dimensional wires that aren't talking to each other at all. Okay, and that would have this would be finite. Okay, and so it doesn't distinguish that between an isotropic Fermi liquid that is entangled in all directions. So we want something else. So the idea we had, so we have this, the problem is this area law, and the reason it's an area law is because the boundary scales with the area, right? And so now that wasn't a problem in one dimension because the two regions, they meet at a point which doesn't have an area. And so what we need something that gives us a point in 2 and 3 dimensions, and in 2 dimensions. Generically, 3 regions meet at a point, and in three dimensions, generically 4 regions meet at a point. I don't know if you can parse this picture here, but this is sort of like a 4-dimensional peace sign. Okay, a 3-dimensional peace sign. Sorry. So what we want to do is we want to, this motivates us to consider the 3-partite or 4-partite entanglement. Okay, and so so in order to set the stage for that, let me talk about the bipartite entanglement first. So and so what I'm going to do is I'm going to recast the bipartite entanglement as a kind of mutual information. Okay, so I can define the mutual information between 2 regions to be this, and now this doesn't really have any new information in it because for a pure system, if the whole system AB is in a pure state, then SAB is going to be equal to 0, and SB and SA are going to be equal to each other. So this is really kind of the same thing as the up to a factor of 2. This is the same thing as the bipartite entanglement. But this is the thing we're going to generalize to the multipartite entanglement. And so the way we calculate this is sort of the standard. So the von Neumann entanglement entropy is going to be the trace of the rho log rho, where rho is the reduced density matrix, and one can deal with this log by doing the replica trick. So there's a trick for doing that. And if you do this replica trick for free fermions, there is a simplification that arises, which is that this mutual information can be written in terms of the cumulants of the equal time particle number correlations. So basically there's an expansion in powers of the charge in regions A and B, and what this mutual information and moreover, it's the log is contained in the first term of that cumulant expansion. So you only need to keep the first non-zero term in this expansion, and that gets the universal logarithmic behavior. And so what that tells us is that what we can do is we can compute the equal time number correlations between region A and region B. And that is related to this mutual information. And that in turn has this log in it. The way we can see that it gets the log is that the equal time number correlations are related to the integral of the equal time density correlations. And that's what I was talking about to Clay before. And this thing has a universal behavior. Okay, so the equal time density correlation, and this is a trivial thing to think about in a Fermi gas, because this rho of Q, rho of minus Q, what it basically measures is it measures the volume in momentum space that is inside the Fermi surface but outside the Fermi surface shifted by Q. Okay, because it's not too hard to see that. And so it's precisely proportional to Q. Okay, and so if you then do the Fourier transform and do the integral, then you get this log. Okay, and so that's a way of, this is a simple way of getting this Cardy-Calabrese result for free fermions.
So this formula is require Q less than 2kF, or?
Yes. So what it requires is that Q be small enough. It doesn't have to be much less than 2kF, but it has to be less than some. I mean, so if you have your Fermi surface shifted by Q, this formula will be exact no matter how big Q is, as long as Q isn't bigger than 2kF. So there's a finite cutoff. There's a finite value that Q has to be less than in order for that formula to be exact. Yeah. And this is going to happen in my higher dimensional generalization as well. Okay. All right. So, okay. Now, one other, so when you formulate it like this in terms of this density correlations, then there's a question you can ask, which is whether the electron-electron interactions are going to change the result. Okay, and your first worry might be that, well, you know that the electron-electron interactions will affect this density-density correlation function. I mean, so you're calculating some bubble diagram like this. There's going to be a correction, that looks like this. Okay, but we also know that in a one-dimensional Luttinger liquid, C is equal to 1. Okay, no matter what K is, no matter what the interactions are. Okay, and so it's instructive to understand how in this calculation the interactions don't matter. And so the point is that in this replica theory, one can understand that this diagram and all of the higher diagrams are precisely equal to 0. Okay, and so so we can understand with this type of calculation why it is that electron-electron interactions do not destroy this quantization. Okay. So now, so we want to step this up to higher dimensions. I'm going to first do 3 dimensions before I talk about 2. So, so in 3 dimensions, what we need to do is, again, we need to, have our 3-dimensional piece sign that has 4 regions that meet at a single point. And then what I'm going to do is I'm going to define a combination of the entanglement entropies, which is designed so that all of the bipartite correlations and the tripartite correlations that happen along the line, all of those are exactly canceled off. And that's going to leave only the correlations that involve all 4 regions. Okay, and so what we've done is we've basically calculated this thing, and it has a universal log cubed divergence. Okay, with a coefficient that measures the Euler characteristic of the 3-dimensional Fermi sea. Okay, and so this is a kind of generalization of this Calabrese-Cardy result. Okay, for free fermions. Well, actually, for a Fermi liquid, I'm going to tell you that it's insensitive to interactions. And again, the way we went about computing this was to again use this replica theory, which allows us to write the free fermion entanglement in terms of the cumulants of the number fluctuations. The sort of q squared term exactly cancels in this, okay? And so the first non-zero term in the cumulant expansion occurs at q to the 4th, okay? And in fact, it's basically this correlation, the disconnected correlation between QA, QB, QC, and QT, okay? And so what we showed is that this has this log cubed divergence, and the way we did that was, again, to relate this to an integral of the density equal time density correlations Okay, and so in doing so, we discovered this remarkable fact, which is the fourth order equal time density correlations in a Fermi gas has so it's going to be a function of 3 q's because the fourth q has to add up to 0, and it's given precisely by the triple product of the 3 q's. So this is a sort of a generalization of the thing that we had in one dimension, which is proportional to the absolute value of q. And so I have to say, I'm not sure I fully understand the significance of this result. It seems remarkably simple.
It looks related to the cubic anomaly of the U1 currents. There would be a contact term in the 4-point function of charge densities from that.
Okay, you're going to have to take the cubic anomaly. I don't know what that is.
Well, in 4 space-time dimensions, which is I believe where we are, there's a triangle diagram anomaly, which would give a contact term in the 4-point function of charge densities.
3-point function.
Well, also give the 4-point function by gauging units.
But this one is sensitive to interactions, right? It's this observable, so it's probably not.
Yeah, this is sensitive to interactions. Yeah. Yeah, I mean, you're telling me about things that I don't know, so it could be you have something, but so this is a 4-point correlation function, equal time. I would like to believe that it has something to do with some kind of anomaly, but I don't. That I don't have yet. So maybe you can teach me something. That'd be good. Okay. So in any case, I think this result may offer some other opportunities for I mean, this would be an interesting thing to measure. Okay, the density, in general, you measure the density correlation function by doing scattering experiments, and so this might be something that would be interesting to measure. It's quantized, and it's proportional to something topological. Okay, now
How do you measure the equal time density? How would you measure the equal time density?
well, I mean, so with X-ray scattering, you can measure equal time correlations. I mean,
So they're not at some frequency.
What's that?
They're not set at some. Aren't you measuring some kind of finite frequency response there?
I think. I mean, if you do X-ray scattering on a crystal, you're measuring S of Q, not S of Q and omega. So it's the frequency integrated thing. But I think people who do X-ray scattering know how to measure equal time.
I see. And nonlinear response.
Well, I think now most X-ray scattering is done. You're just measuring S of a single Q, which is a rho correlation function. So there may require some technology to measure, rho. But it doesn't. I'm not sure there is in principle reason why that can't be done. Okay, so I'm sure there are plenty of technical obstacles for the experimentalist to do that. But that's good. That gives them something to do, right? So. Okay, so now of course this fourth order of density response function is affected by interactions, but in the same way as in the 1D case, the mutual information, which we get to take the replica, do the replica theory for, the interaction corrections vanish for the same reason that they did in one dimension. Okay, and so in that sense, this integer characterizing the characterizing the Fermi C really, it distinguishes distinct sort of topological Fermi liquids, if you will. Okay. All right. So let's see. How am I get until I have a minute or two left. Okay, good. So I just want to tell you one more thing, which is quick, which is why I went straight from 1 dimension to 3 dimensions, and what happened in 2 dimensions. So the problem with 2 dimensions, I try to do the same thing, and I get 0. And it's trivial because, if I try to define this tripartite mutual information, mind you, I'm talking about A, B, and C are my entire system, and so and the entire system is in a pure state. So SABC is equal to 0, and then SA is going to be equal to SBC, and SB is equal to SAC, and SC is equal to SAB. So this thing is 0 even before we tried to calculate it. Okay, and maybe that's not a surprise because you'd think that entanglement should be a property of the Fermi surface, not so much as the Fermi sea, right? And as I told you before, in even dimensions, the Euler characteristic of the Fermi surface is equal to 0. Okay, so I think it's probably, maybe it's not an accident that that these two sort of go together. Okay, and so the question is there anything? And another thing is that the Euler characteristic of the Fermi sea. In 2 dimensions, it's the difference between the number of electron-like and hole-like Fermi surfaces. So it changes sign if I exchange particles and holes. Okay, so the Euler characteristic of the Fermi sea is odd under particle-hole symmetry. Whereas, obviously, the entanglement entropy is going to be even. I mean, the entanglement entropy doesn't care whether it's electrons or holes. Okay, so there's no hope of ever getting anything that's going to be proportional to the Euler characteristic of the Fermi sea by talking about the entanglement entropy. So we need to have something else. And so what we came up with is a kind of modification of the entanglement entropy, which is weighted by the charge in each region. Okay, so this is something we can define. It's something we can compute, and the calculation of this is almost exactly the same as the calculation I did before. The only difference is that instead of picking out the even cumulants of the charge density, q squared, q to the 4th, it picks out the odd cumulants of the charge density, and it's odd under particle-hole symmetry. And so this charge-weighted mutual information, which I can define from this, just by doing this with q's on all of these, then this has a log, and this is related again to the universal density correlations in 2 dimensions, which so this, for a free Fermi gas in 2 dimensions, there's these universal equal time density correlations. In this case, is q1 cross q2 absolute value. Okay. And again, maybe this is something that one could do in a 2-dimensional electron gas, some scattering experiment to measure this. That might be an interesting thing. Okay. Now, one thing about this is that this charge-weighted entanglement entropy, charge-weighted mutual information, if we go back and ask what's the effect of electron-electron interactions, then the argument that got rid of them for 1 dimension and 3 dimensions doesn't work anymore, okay? Basically because some of the bubbles that we calculate are different because they involve this Q rather than the Q's from this. And so, so the upshot of that is that this charge-weighted mutual information is not as robust as the as what we had in 1 and 3 dimensions. Okay, so I think that's about it. So let me just conclude. So the main lesson here is that the Fermi sea is a topological object. Okay, it has a topological invariant associated with its shape, and so we showed that this is reflected in a quantized nonlinear conductance, with some caveats. Okay, and it's also reflected in the multipartite entanglement. And in 1 and 3 dimensions, this I think is really telling us something deep about the Fermi liquid phase. Okay, so I think another open question is whether there are other probes of the topology of the Fermi's surface. And taking our inspiration from one dimension, there's another quantized response in one dimension, which is quantized thermal response. Okay, and we know that the quantized thermal response measures C. Okay, and is insensitive to interactions. It makes you wonder whether there's something like this in higher dimensions. Okay, and so that would be an interesting thing. Can one measure low frequency correlations in the charge? Okay, is there noise measurements that could reflect this this quantity? Or as I said, equal time density correlations. Maybe one can do some version of X-ray scattering to measure the universal topological correlations in a Fermi gas. Okay, so thank you very much. Yes.
Yeah, so I was wondering if, basically, how big is this effect? So take your toy model, sort of where you, or the toy setup where you pulse, the one region, the second region you measure in the third region. If you were to send, say, like 10 to the 10 electrons through, in each pulse, what would you expect the order of the effect to be?
Well, okay, yeah, so, right, now, the number of electrons that you're sending through, I presume is going to scale with the length of your contact, right? So in this response that I defined, one has to be careful because we're subtracting. So what I'm doing is I'm asking what's the charge that flows into the region if I do both pulses, and then I'm going to subtract the charge that I get if I just do one pulse by itself and the charge if I get the other pulse by itself. Okay, and so the things that I'm subtracting scale with the length. Okay, whereas the residual does not scale with the length. Okay, so the answer to the question depends a little bit. I mean, you didn't give me enough information because you didn't tell me what the length was, right? I mean, so what I can say is that I can tell you that the value of this conductance is going to be, e cubed over h squared divided by this. Well, it's basically going to be e cubed over h squared. If you do these h over e voltage pulses, then e cubed over h squared is going to tell you the scale for how many electrons you get.
Yeah, I guess what I want to know, like say all your assumptions hold, where you have all these the things that make it hard for the experiment, like the interactions, whatever. Say you had all that. Like I was curious if it's a big enough effect to be like, would it be obvious it's there if you had all those conditions? Like,
The honest answer is I don't know.
Okay. Yeah. Okay, thanks.
Yeah.
Yeah. Do you know how the multipartite entanglement looks in a thermal state? The volume law cancels, I guess.
Yeah, I think it does. Yeah. So you're saying at finite temperature.
Yeah.
Yeah. Yeah. So there, of course, you need to include the SABCD. You need to include that as well. And so I think that the volume law pieces are going to all get canceled out by that.
Right.
So the mutual information trick cancels out. So even in one dimension, if you calculate the mutual information SA plus SB minus SAB, then I think at finite temperature you still get the log, right?
Yeah, I'm asking because one of the arguments for the fact that entanglement, just the simple entanglement entropy doesn't depend on interactions. It's probably not the strongest argument, but it's some scaling with so at finite temperature. You expect the entanglement the entanglement entropy to be some scaling function of temperature times length times the appropriate constants.
Mm-hmm.
And at finite temperature, it's given by the entropy of a Fermi liquid, which doesn't depend on Landauer parameters. And then if you have maybe put in some assumptions about what the scaling function looks like, you might expect that it never depends on Landauer parameters. Also
Well, no, but isn't the entropy of the Fermi liquid in the term that gets canceled? I mean,
so here I'm talking about just for the regular entanglement entropy. Let's
Yeah.
say I have, let's say I just have the entanglement entropy of one region, A.
right.
So and this at finite temperature is going to be some scaling function of temperature times the size of the region. So the limit where temperature goes to 0, it's given by the Widom formula, which probably doesn't depend on Landau parameters. But in the limit where temperature goes to infinity compared to the system size, the size of there it's given by the thermal entropy of
Right.
But by volume law and
Right. Yeah.
and in that limits we know there are no Landau parameters because that's just the thermal entropy of the Fermi liquid, which doesn't have
I see.
contributions. That's like one argument for
I see.
it's not the scaling function could depend on Landau parameters for some reason, so it's not completely obvious that it's solid, but
I mean, but I guess, but you agree that that when you push it into that limit, it's almost going to be completely canceled by doing the subtraction.
Yeah, in this way, that's right. Yeah. So you might expect that it's still some kind of log, and that's why I was asking.
I think so. Yeah.
Yeah,
Michael.
Just one question. So you said you like to think of these regions as filling up all of space. Is that important, or can you have them?
Well, no, it's not. It's not essential. But if so I could imagine that I have a three-dimensional version of this picture, right? So I have a region E outside A, B, C, and D. But then it would be essential that I include this term. And so actually that question is not completely different from the question of what happens at finite temperature, right? Because because the point is that A, B, C, the A, B, and C will be in a mixed state, right, if I trace out region D. Right. Yeah.
There are no more questions. Let's thank Professor Kane.
Thank you very much.